Error handling in banking systems. In this lesson, we will learn how to handle errors when processing banking data in Python. Error handling is important in banking because even small mistakes in code or data can lead to financial losses and compliance issues. You will discover how to identify, handle, and debug different types of errors that commonly occur in banking applications. By the end, you will be confident writing safer banking code and debugging real-world financial data. Running the cell now. We import pandas so we can work with tabular data. We import NumPy for numerical operations and random sampling. We import warnings to suppress less important warning messages. We ignore warnings to reduce distractions while we learn. We set NumPy's random C to 42 so our results will be reproducible. Running the cell now. Overview of data used in banking error handling. Banking data includes transactions like withdrawals, deposits, transfers, and more. Data is usually structured in tables, with columns for customer IDs, amounts, dates, and transaction types. Beginners often make mistakes like working with missing values, wrong column names, or mismatched data types. Running the cell now. We will now generate sample transaction data for this lesson. We create a synthetic data frame to simulate banking transactions. We set the number of transactions to 1,000. We set the number of customers to 200. We start building our data frame. We add a unique transaction identifier for each row. We assign each transaction to a possible customer. We create random but realistic transaction amounts, with some variability. We specify whether each transaction is a debit or credit. We randomly assign each transaction to a banking channel. We create a date-time index representing transaction times. We finish the data frame with all our generated columns. We print the shape so we know how much data we have. We preview the first 3 transaction records. Running the cell now. This output shows a synthetic banking transactions table with 1,000 rows and 6 columns, illustrating typical data fields like transaction ID, customer ID, amount, type, channel, and date. Notice the variety in transaction types and channels, which mimics real-world banking data to prepare for common beginner errors like handling missing or mismatched data. This setup helps learners understand the structure and complexity of transaction datasets before diving into error handling. Try changing the number of transactions or customers to generate a larger or smaller dataset. Now let us see what happens if we try to use a column that is not in the data. We attempt to print a balance column, which does not exist in our data frame. We wrap the operation in a try-except block to catch errors. This line is where the error could happen. If a key error occurs, we catch it and print the error message. We display the error to understand what went wrong. Running the cell now. This output shows a key error because the code tried to access a column named a balance which does not exist in the dataset. This highlights a common beginner mistake of referencing incorrect or missing column names, emphasizing the importance of checking column names before accessing data. Practice: try changing the column name to another name that is not present in your data to see what error you get. Let us look at another common mistake, dividing by 0 when processing numerical data. We try to create a new column by dividing transaction amounts by 0, which is not allowed. We use a try-except block so our code will not crash. This is where the division happens and could raise an error. If there is a division by 0, we catch the error and show a message. We print out the error for learning. Running the cell now. Practice: what happens if you divide by a very small number instead? Sometimes data comes in with the wrong format. Here is how a conversion error appears. We create a column with all string values that cannot be converted to floats. We use a try-except block to catch value conversion errors. This line tries to convert strings like 100 to float, which will fail. If a value error happens, we catch and display the error. We print the error so it is clear what went wrong. Running the cell now. This output highlights a common beginner mistake when converting data types in transaction tables. Here, trying to convert non-numeric strings to floats causes a value error. Notice the error message clearly points out the problematic value of 100, demonstrating why clean, numeric data is crucial for accurate financial calculations. This example reinforces the need to validate and prepare data before applying type conversions in banking data workflows. Try changing one of the values to something like the 100 and see what happens. Banking data often has missing amounts. Let us see how to handle missing values with simple error handling. We copy our transaction data frame. We set the amount column in the first few rows to missing NaN. We use try to attempt calculating a total. We try to sum the amount column, and pandas will skip NaN values. We print the total transaction amount. If there is any general error, we catch and print it. We always print out errors for diagnostics. Running the cell now. This output shows that summing a column with missing values still works without error, as NaNs are ignored by default. Notice the total amount reflects the sum of all non-missing amount entries, demonstrating how pandas handles missing data gracefully. This reinforces the lesson that beginners should be aware of how missing values affect calculations and when explicit handling might be needed. Try changing the range of missing values or using .mean instead of .sum on the column. Banking systems should not have transactions with negative amounts for debits and credits. Let us check and fix this. We locate all rows where the transaction amount is negative. If any negative amounts are present, we print a warning message. We let the user know that we will correct the negative amounts. We set all negative amounts to 0 so the data is logically correct. If there are no negative amounts, we print a success message. Running the cell now. This output shows the code successfully detected negative transaction amounts, which are errors in this banking dataset since amounts should be positive. The message confirms the presence of such invalid values, and the code then corrects them by setting those amounts to 0. This illustrates the important step of error handling to ensure data integrity before analysis. Practice, try manually introducing negative values and rerunning this cell to see the fix in action. In real banking code, errors should go to logs, not just the screen. We will set up basic file logging now. We import the logging library to record error events. We configure the logging to save errors to a file named banking_errors.log. This line is just a blank line for clarity. We try to convert transaction_ID to float, which should work at first. We intentionally assign a string to the first row to create a conversion error. We attempt to convert the column to integer values. If there is any exception, we print a message indicating the error is being logged. We log the error message with details to banking_errors.log. Running the cell now. This output shows an error caused by trying to convert a non-numeric string, error_ID, to an integer in this transaction_ID column. The key takeaway is that the code correctly catches this conversion exception and logs the detailed error message to a file, illustrating effective error handling in banking data processing. This practice helps maintain data integrity while debugging issues like mismatched data types, which are common in real-world banking datasets. Let us open the log file so you can see how error messages are recorded during banking operations. Prompt: open the log file to see how the error was recorded. We can use the assert statement to enforce business rules directly in the code. This is often done in banking to stop processing if rules are violated. We check that every transaction amount is at least 0. If the rule is followed, we print a success message. Running the cell now. This output confirms that all transaction amounts in the banking dataset are 0 or positive, aligning with the key business rule that transactions can't have negative values. The assertion helps catch errors early by ensuring data integrity, which is crucial in financial contexts where incorrect amounts could lead to faulty analyses or system failures. Try removing the earlier negative value check and observe what happens if negative values are present. Let us see how to handle more than one possible type of error at once. We use try to detect errors that may occur. We purposely print a row that does not exist to cause index error. We catch and print an index error if it happens. We can also catch any other error and print it as well. Running the cell now. This output shows an index error caused by trying to access a row at position 5000, which doesn't exist in the dataset. It highlights the importance of handling different exceptions when working with banking data tables, as indexing errors commonly occur if assumptions about data size are incorrect. This teaches beginners to anticipate and manage specific errors to make their code more robust. Practice: try changing the row number to an existing index and see what prints. Advanced: sometimes you will want to define your own error types. You might do this for special banking rules, like detecting suspicious activity. We define a new exception called suspicious transaction for special banking issues. This pass statement just means our custom class has no extra code. A blank line for clarity. We define a function to validate that an amount is not excessive. If an amount is above 5,000, we raise our custom exception. A blank line for readability. We use try to see if a test value is caught. We test with a transaction of 6,000, which is suspicious. We call our function, which may raise our custom error. If our custom exception is raised, we print a warning. We display the custom exception warning. Running the cell now. This output shows a custom exception being raised when a transaction amount exceeds a set threshold, which in this case is 5,000. Notice how the error message clearly indicates the issue with the transaction, illustrating how custom exceptions help catch and handle specific data validation problems in banking workflows. This reinforces the lesson's point about proactively managing errors in transaction data to maintain data integrity. Practice: try modifying the threshold and test amount to explore this logic. Advanced: in banking, you often process large batches of transactions and need to collect all errors, not just fail on the first error. We define a function for batch transaction processing with error handling. We create a list to store errors as they happen. We loop through every row of the data frame. We use try to check and catch issues for each item. We check if the amount is negative, and if so, raise a value error. We add a type error at a specific index to test robustness. If there is a problem at index 13, we create a type error. Any exception is caught and added to our errors list. We continue to the next item without stopping the batch. The function returns a list of all errors caught. We create a list of batch errors by calling our function. We print out the first few errors to review them. Running the cell now. This output shows the detected errors during batch processing of transactions, specifically highlighting a type error at index 13 where a string was wrongly concatenated with an integer. Notice that no missing or negative amounts triggered errors here, indicating the code's focus on catching unexpected data type issues and custom validation. This reinforces the lesson's point about anticipating and handling diverse error types when working with transaction data. YouTube: search a Python try except in real projects to see expert handling of batch errors. The finally clause lets you run code no matter what happens in try or except. This is useful for closing files, database connections, and cleanup in banking scripts. We attempt a risky division that will always fail. We catch division by 0 and print a warning. The finally block runs whether or not there was an error. We print a message indicating that cleanup code has run. Running the cell now. This output shows how the finally block runs regardless of whether an error occurs, in this case, a division by 0. Notice that the error message prints first, followed by the cleanup message, ensuring important code always executes. This illustrates robust error handling, crucial in banking data workflows to maintain data integrity even when problems arise. Practice: try removing the error and seeing if the cleanup message still prints. Debugging banking data, locating common errors. When your code fails, focus on the error message and the data used for that code. Print and df.info are your best tools for finding issues. In banking, errors can waste time or even stop trading or payment batches. Running the cell now. This code helps you verify data types and see if any columns are missing values, critical before any finance calculation. We print data frame info, including types and how many non-null values per column. We print the total number of missing, null, entries in each column. Running the cell now. This output shows the structure and completeness of the banking dataset, confirming it has 1,000 rows and 8 columns with no missing values, a crucial first check for data integrity. Notice the unexpected object type in the error_amount column, which should likely be numeric. This signals a potential data type issue to investigate further. Using df.info and df.isnl.sum helps quickly identify such discrepancies, essential for debugging errors that could disrupt financial operations. Prompt: always use .info and .isnl.sum before applying business rules or formulas. Best practices for error handling in banking. Always catch exceptions when reading, writing, or transforming financial data. Validate inputs, outputs, and intermediate values. Use logging for serious problems, not just print. Assert business rules early and test boundary cases. Running the cell now. You should always give clear error messages for banking system users. We use try to attempt converting user input to an integer. If the input is not a number, a value error occurs. We print a helpful message guiding the user to fix their entry. Running the cell now. This output clearly shows a context-specific error message triggered by a value error when trying to convert non-numeric input to an integer. It highlights the importance of catching exceptions to provide meaningful feedback to users, as emphasized in the lesson's best practice of handling errors gracefully in financial data processing. This approach helps prevent confusing raw errors and improves user experience in banking applications. Practice: experiment with different invalid entries and see how the error message changes. Including the transaction ID in error messages helps detect and fix data problems faster in banking. We loop over the transactions, processing each one. We use try to attempt to convert the amount to an integer. If there is an error, we print the transaction ID and error message. We stop at the first error to avoid flooding the console. Running the cell now. YouTube, search Python banking error handling best practices for professional advice. Let us combine what we have learned. We will validate our data and save valid or invalid transactions to separate files. We define a function for validating and saving transactions. We keep an errors list for rows with issues. We also keep a list for valid transactions. We loop through every transaction one by one. We try to convert the amount and require it to be non-negative. If successful, we add the row to our list of valid transactions. If anything goes wrong, we store the transaction ID and error. We save valid transactions to a CSV. We save all errors to a separate CSV for investigation. We call our validation function with our main data frame. We print confirmation that files are written. Running the cell now. The output confirms that the function completed without crashing, highlighting successful exception handling during validation and file writing. Notice how invalid transactions are captured in a separate errors file, reinforcing the lesson on separating error tracking from valid data processing to maintain data integrity. This approach ensures robust handling of financial data by validating inputs and logging issues systematically. Opening the transaction errors file so you can see which records failed validation and why. Now open transaction_errors.csv to see what went wrong for any transactions. Let us preview the first few valid transaction records saved after error checking. We read the valid transactions file into a new data frame. We show the first 3 rows so you can check that only clean data was saved. Running the cell now. This output preview reveals critical issues in the valid transactions file, such as an invalid transaction_ID, error_ID, infinite percentage values, and non-numeric error_amount. It highlights the importance of validating file contents and catching data quality errors early, as emphasized in our lesson on input validation and error handling in banking data workflows. Let us open the file containing the valid transaction so you can view the clean data. Try opening the file directly in your File Explorer for a closer inspection.